In this video, we'll walk through two attack paths that represent common real-world patterns in OT incidents. For each one, we'll trace the attacker's steps in detail, and then we'll identify the specific controls from this course by module that would have stopped the attacker at each stage. The goal is to make the connection between the concepts we've covered and the actual scenarios they protect against. Let's look at the first scenario. In this scenario, an attacker sends a phishing email to an office employee. The email contains a malicious link. The employee clicks it and their workstation is compromised. The attacker now has control of a machine on the enterprise IT network, level 4 in the Purdue model. From that workstation, the attacker runs network discovery tools. They find a historian server with two IP addresses, one on the IT network and one in the 10.10.x.x range that looks like OT addressing. The historian was configured with a direct interface on both networks for convenience. It receives data from OT and makes it available to IT without going through a DMZ. The attacker connects to the historian through its IT interface, escalates privileges using stolen credentials cached on the historian from an engineer's previous remote session, and from the historian's OT interface begins scanning the OT network. They discover PLCs listing on port 502, Modbus, with no authentication. They can read all register values and write to any register. Full access to process control reached from a phishing email on a corporate workstation. 3 controls would have broken this attack chain at different points, and any one of them would have been sufficient to prevent the outcome. The first control they could have incorporated was the historian should not have been dual-homed. It should have been placed in the DMZ with controlled connections in both directions through firewalls. A historian in the DMZ with no OT side interface means the attacker who reaches the historian never reaches an OT network directly. This is Module 4. The DMZ architecture specifically exists to prevent this exact scenario. A second control they could have incorporated would be a firewall. Firewall between the IT network and OT should have blocked the attacker's reconnaissance and connection attempts. Even if the historian was in the wrong place, a default deny firewall at the IT-OT boundary with no rule permitting historian to PLC connections on port 502 or any other port would have blocked the lateral movement from the historian to the PLCs. This would be Module 5. The third control they could have implemented would be a network monitoring platform in OT would have flagged the unusual communications. A device, the historian, that normally communicates with specific PLCs on specific patterns, suddenly issuing different types of queries at an unusual time. This is Module 6. The attacker succeeded because none of these controls were in place, and each one independently would have stopped the attack before it reached the PLCs. Let's look at a second scenario. A vendor requires RDP access, port 3389, to an HMI for remote monitoring and support. The firewall administrator opens inbound TCP port 3389 from any source, meaning any IP address on the internet can reach this HMI's RDP service directly. The vendor was given a username and password that had never been changed from the system default. An automated scanner running continuously, scanning the internet for open RDP ports, discovers this HMI within hours. A credential stuffing tool tests thousands of common username and password combinations. The default credentials match, and the attacker authenticates successfully. They now have an interactive Windows session on the HMI, the full operator interface for a SCADA system. They can see real-time process data, can issue commands to field equipment through the SCADA interface, and have access to any files on that workstation. This is not a sophisticated attack, it's fully automated, it requires no special knowledge of OT and no targeted research. It's the same automated attack that's used against thousands of internet-exposed RDP targets every day. 3 controls, each of which independently would have prevented the attacks. The first one, if they would have restricted inbound RDP from the internet. This is a hard rule. Vendor access should have been established through a VPN to the DMZ, authenticated with MFA, and then RDP from a jump host within the controlled network. The HMI's RDP port should only have been reachable from the jump host IP, not from the internet. This is back in Module 5, Secure Remote Access. A second control would have been multi-factor authentication. Default credentials combined with MFA would still have stopped the attack. The attacker would have the username and password, but not the second factor, the authenticator code or hardware token. Credential stuffing fails against MFA even when the password is correct. This is Module 5. A final third control they could have implemented would have been change management for credentials. Default credentials should have been changed before the system was connected to any network. Vendor accounts should have unique credentials, not manufacturer defaults. This is basic access control that doesn't map to a single module. It's foundational practice. The pattern in this attack path is its frequency. Internet exposed RDP with default credentials is one of the most documented initial access techniques in ICS incidents. The fix is straightforward and well known, and the fix has been available for decades. Attacks of this type succeed because the straightforward fix isn't applied, not because the attackers are sophisticated. In the next video, we'll cover 2 more attack paths: an unpatched HMI with legacy services, and a supply chain access scenario that's become increasingly common in OT incidents.